Welcome to part 18 of the video series on probability distribution. In this video, we are going to talk about Weibull distribution. Now, it is a distribution which is not commonly described in different tutorials or in different blogs. But trust me, if you are working with bioinformatics data and survival analysis, then you are going to encounter Weibull distribution. So, I am going to describe the distribution in detail today, and hopefully after this, you will not have any problem working with this distribution. So let's dive in. So first, let's talk about the probability density function. First thing to note is that this is a continuous distribution. That is why we are looking at the density function. The function looks quite hideous, I know, but actually in reality, it is quite simple. Let me break this down. First of all, you have the random variable x, and you can see x is actually sitting up here and here. And there is a term which is a multiplicative term, and there is the exponent term. And there are three other parameters right here which you have to manually define. So you have to manually set the value of k, set the value of lambda, and set the value of theta as the parameters of a particular PDF function. Now you can see the k, theta, and lambda right here in different places. Now I am going to talk about these three parameters in more detail in the next few slides. But in this slide and right now, just remember that your x, your random variable, has to be greater than or equal to theta, which is this one. If x is less than theta, then the value of this function, the density of this function will be 0. Now, although this function looks quite daunting, for k equal to 1, lambda equal to 1, and theta equal to 0, which you can think of as base case, this entire function will reduce down to e to the power minus x, which is extremely simple. That means basically this entire hideous function is an extension of e to the power minus x. So the three parameters k, lambda, and theta are known as shape, scale, and location respectively. Let's now talk about the simplest of the three parameters, which is the location or shift theta. You can see that theta is something that is being subtracted in both places where we have random variable x. If you know about plotting and functions, you know that this is a translation parameter. What do I mean by that? If theta equal to 0, so suppose a shape and scale are fixed, and we basically change the theta and see how the plot looks like. You can see that when theta equal to 0, the function plotting starts from 0. Everything to the left is 0. When the location is minus 50, the function PDF plot starts from minus 50 and everything to the left will be 0. Similarly, when location theta is 50, the function starts from 50. So this parameter theta is basically responsible for where your PDF plot will start from. And it is unrestricted. You can give it any real number. So negative value is also okay. The next parameter is scale lambda. You can see that these are the lambdas, and lambda is nothing but a divisional factor. So what does divisional factor do? It scales the function. So you can see for the same shape and the same location theta, if we vary the scale, the bigger scale we have, the more stretched the function PDF looks like. The value of lambda can only be greater than 0. Obviously, it cannot be equal to 0 because for lambda equal to 0, this function will be undefined. If you have negative value for lambda, then this density can become negative. And negative density does not really have any real physical meaning. Finally, we have shape k. So these are the k's. Now it is very hard to understand why k actually determines the shape of the function. But if you do plotting, so let's first fix location and scale to 0 and 10, and then let's vary the shape. So any shape value that is less than or equal to 1 will look like an exponential distribution. Shape values from 1 to 2.5 will look like a right skewed distribution. If you increase the shape even further, it will look like a fat-tailed T distribution. Again, if you increase it even further, then it will look like a normal distribution, and the distribution will become more and more like closer and like steep if you increase the shape parameter k. So basically the standard deviation is decreasing. So if you want to learn more about this distribution, like t distribution, normal distribution, and also the ones I showed you before, you can follow the video series because it describes all these distributions in more detail. So basically, the moral of the story is by tuning k, by changing k, you can actually make the Weibull distribution approximate different kinds of probability distributions. That is the beauty of Weibull. So your k or shape parameter has to be greater than 0. Otherwise, your probability density function will not integrate to this will be 1. I'm sorry about this. This will be 1. Otherwise, the probability density function will not integrate to 1. Next up, let's talk about the cumulative density function CDF. Now for this PDF, we are not going to talk about the mean and variance because that is not actually very important in a practical sense. But the CDF is actually more important, so I am showing the CDF here. So you know what the CDF is. So CDF f of x is equal to the density at x greater than less than equal to x. That means what is the probability of random variable x being less than or equal to small x? That is basically nothing but the CDF at value x. So if your x is greater than or equal to theta, that means it is in the valid range, then this CDF will be integrated from theta to x. I mean, normally you would integrate it from 0 to x or minus infinity to x, but you know that anything below theta, below location is 0, so you can integrate from theta to x. And this will be the PDF, ft, and then dt. If you do the integration, you are going to get something like this. Now, if your x, I mean this x value is less than theta, then this fx will be equal to 0. Anything, because any region where your random variable is less than theta, the PDF of the Weibull distribution will be defined as 0. There is a special case. Suppose your location parameter is 0, that means your whole plot starts from 0 and your x can be greater than or equal to 0. In that case, what happens is this CDF will turn into this simpler version of CDF. Now, why am I actually showing you this? Because this form right here, you are going to see it in many places when you do survival analysis. In survival analysis, there is an important concept called hazard function, which signifies the probability of survival beyond time t, given that survival occurred up until time t. So basically, what is the probability of some patient surviving beyond time t, given that he has already survived up until time t? That is the hazard function. Now, the hazard function is closely associated with the value of k, with the choice of k. Let me explain. I mean, I am not going to show you any formula here because this is not a series on survival analysis, but I just want to make some notes. So I just want you to know that if k less than 1 in the hazard function, which is often represented by the Weibull distribution CDF, in that case, hazard will decrease over time. That, for example, in case of infant mortality, as more time passes, the chance of survival of an infant increases, right? That means hazard decreases basically. Hazard decreases. Also, organ transplant rejection. So, as more days pass after the organ is donated, the donated organ will be less and less likely to be rejected. That means hazard decreases. So you can very easily model these kind of things by choosing an appropriate k of less than 1. If you choose k equal to 1, then hazard is constant over time. For example, lightning strikes. It doesn't depend on time. It is very random. Radioactive decay is also very constant. It is not going to change as time passes. Also, the most interesting case I think should be of k greater than 1 because if you are working with patients with disease, then k should be greater than 1 because patient survival, the chance of survival typically decreases over treatment period, right? That means hazard increases. Also, if you are working with machineries, reliability engineering of machines, you know that machines tend to get increasing probability of errors with age. That means hazard increases over time. So in this way, you can model a hazard function and survival analysis using Weibull distribution. So thank you very much. If you like the video, feel free to subscribe and share. And also we have a Link in the description for donation. If you want to support our effort, you can donate to our channel. Thank you very much.